In this problem, we have two metal balls, and each one of them carries a different electric charge. They are attached to one another by a taut 2-meter long string, which means that the distance between the two balls is fixed. And if the positions of these balls relative to one another is constant, then that means that we can apply the Coulomb's law, which gives us the electrostatic force for two electrically charged objects that are not moving with respect to one another. And according to Coulomb's law, the electrostatic force between two such particles is equal to the Coulomb constant K multiplied by the product of the charges on the two particles. Now in this case we're told that the charge on ball A is Q, and we're told that the charge on ball B is 2Q. And this is divided by the square of the distance between the two charges, so the square of what I will label R. Now the problem actually already provides the electrostatic force between the two particles. In part A of the problem, it's given as 2.5 newtons. What part A of the problem is actually asking for us to find is the magnitude of Q, this charge. So what we should be doing is algebraically rewriting this equation to solve for the variable Q. Now first things first, I do want to simplify this slightly because we have a Q multiplied by a Q in the numerator of our Coulomb's law based on the charges we've been given. So I'm going to rewrite that as a Q squared. So we can see here we've got a K times Q times 2Q. So we can rewrite this as 2 times K times Q, or Q squared divided by R squared. And all of this is equal to F. So if our goal is to solve for Q, we're going to need to do some algebraic rewriting. So we can multiply both sides of the equation by R squared, and divide both sides of the equation by 2K, to get Q squared on its own, which tells us that Q squared is equal to F multiplied by R squared divided by 2K. And lastly, to solve for Q, we're going to want to take the square root of both sides of the equation. So Q is equal to the square root of F multiplied by R squared divided by 2 multiplied by the Coulomb constant K. So now all that's left for us in part A of the problem is to plug in the numerical values that were given to us in the problem. So this is the square root of the force between the two particles, which is given in the problem as 2.5 newtons, multiplied by the square of the distance between the two particles. This is equivalent to the length of the string, so that's 2 meters, and don't forget to square it. And then this is divided by 2, multiplied by the Coulomb constant, which has a value of 8.99 times 10 to the power of 9, with units of Newton meters squared per Coulomb squared. So we put this into a calculator and we find a charge of about 2.36 times 10 to the power of negative 5 coulombs. Alternatively, it would be more proper for us in a case like this to rewrite this value using a proper unit prefix. What we can do is adjust the decimal point one position to the right so that the exponent has to be moved one value downwards, so it'll become a negative 6. And recall that when we have a times 10 to the power of negative 6, that is equivalent to the unit prefix of micro, represented by the Greek letter mu. So our answer can be written more properly as 23.6 microcoulombs. And that is the answer to part A of the problem. But part B of the problem goes a bit further on a conceptual level and asks what will happen to the system over time. This part of the problem is a bit trickier, at least conceptually, because you can't really answer this part of the problem by thinking about the two balls alone. You have to consider the scenario, the surrounding setting of this system. And according to the problem, these two balls are positioned floating between two metal bulkheads. And if you don't know what a bulkhead is, you can just kind of think of it as a wall or a partition. But the implication here in the problem is that since these bulkheads, since these walls are metal, we're meant to assume that these bulkheads, these walls, are conducting themselves, even if those walls don't necessarily possess a charge themselves. So if we have these two charged balls, ball A and B, if we have these charged balls positioned near these bulkheads, then the electrostatic charge from the balls will be inducing a charge in the conducting bulkheads. Because remember that if we have a charged particle near a conducting material that's not necessarily charged, then an opposite charge will be induced, which leads to an attractive force. So the charges from ball A and B will be inducing opposite charges in the bulkheads, creating an attractive force in either direction. But what's really important here is that since ball B has a charge with a greater magnitude than the charge of ball A, this means that the attractive force between ball B and one of these bulkheads is going to be stronger. And if the strongest attractive force is between ball B and the nearest bulkhead to ball B, then the way this system will change over time is that the system will slowly move towards the bulkhead that was closer to ball B to begin with. So, therefore, the answer to what will happen to the system over time is that the system will move towards the bulkhead closer to ball B. And that is the answer to this problem. I hope this video helped you out. If it did, please consider subscribing, as that'll help me out in making more videos just like this. And if you have a request or a question, leave a comment down below, and I'll do my best to help you out as best I can. That's all for now, and I hope you all have a lovely day. Bye-bye.